All right, so I wanted to give you a little help with the problem where you're like driving along. So let's see here, make a bigger dot there. So you're driving along. Oh, those are huge dots. I don't want them that big. Let's try that again. There, maybe that one's good. Or something like that. There. Okay, so you're driving along. Still bigger. There. So you're driving along at 25 meters per second, okay? And there you are cruising along, and then you see danger. And you know what? I'm going to spread those dots out more. Sorry about that. So you see danger. You see a little kitten in front of you or something, okay? And what do? You quickly slam on the brakes. So at this moment here, actually, you see the danger way back here. So you see danger. But it takes you a half a second to react. So your velocity, while you're reacting, well, you haven't started slowing down yet, your velocity is constant. Then, this is when your car is actually slowing down. See, the arrows are getting shorter, right? And then I'll draw acceleration arrows, right? So I'll show over here, I'll show acceleration equals 0. This is called constant velocity, right? Okay, and then over here, while you're slowing down, your accelerations are in the opposite direction, but it's constant acceleration, meaning that your acceleration is not changing. So I'll draw my acceleration vectors there, velocity there. So my velocity arrows get shorter. This is while I'm moving with constant acceleration, and we called it constant acceleration even though you're slowing down. Okay? So there's my constant acceleration. So I got a period of time when I'm moving with constant velocity, and I got a period of time when I'm moving with constant acceleration. Okay? Now draw some stacks of graphs. All right, so I'll draw a position time graph, a velocity time graph. You know what? I could make my graphs a little bigger, don't you think? So position, velocity, and acceleration, right? Position, we say x. Velocity, we call v. Acceleration, a. Time. Okay, and I got the same dotted lines. Okay, so at this moment in time, that's the moment where your motion changes. See, you were moving with a constant velocity. Looks like that. That was your constant velocity. But then you slowed down to a stop. This is your constant acceleration part. And in that part, your acceleration is negative because your slope of your velocity graph is negative. In this part here, your acceleration is 0, since the slope of your velocity graph is 0. On our position graph, while you're moving with constant velocity, you have a line, right? And then while you're slowing down, your slopes have to gradually get less steep. Don't make the mistake of having the slopes go negative like this, because that would be wrong. That would mean you put the car in reverse and you start speeding up in reverse. That's not what we want, right? So your last slope on your position time graph should be horizontal, meaning you stopped, okay? Now we can start solving things. This was, I'll put units on here, meters per second, seconds. This is seconds. This is seconds. This is meters. And that's meters per second. This is meters per second squared, right? Now, if I look at, I think this part here is 25, and my final velocity is 0, right? So And we also know that it takes half a second before you start to even slow down. So half a second is the time where you see the danger at 0 seconds, but then it takes you half a second to react, and then it takes you 3.5 seconds to actually slow down. So you're at 4 seconds by the time you finally stopped, right? So I can do a lot already. I can find the slope. That's going to be my change in velocity divided by my change in time, right? And I could take my final velocity in the end, v2 minus v1, and divided by t2 minus t1, right? And my final velocity looks like it's 0 minus my beginning velocity is 25. So this is going to be minus 25 meters per second. And that occurs over 3.5 seconds, right? So that's minus 25 over 3. Now I'm just going to approximate that. If it were 24, it'd be 8, but 3.5, it's going to be like 7.1 is my guess. Okay, so I'm going to say equals -7, roughly. I'm going to say approximately equal to 7.1 meters per second for every 1 second. So I'm going to be slowing down about 7 meters per second slower each second. So this looks like it's about -7.1, right? And then this is 0.5 seconds, and this is 4 seconds, right? This area here is going to be equal to my positive 25, right? So, because that's my change in velocity. So that area is my change in velocity, which is going to be -25 meters per second. I already know my acceleration. I already know my time to slow down. There really isn't anything to solve there. Now I can find the total displacement right here, right? I can take this area. Maybe I should do that in another color. I'll do that like in white. Okay, this area. So that's half of 25, right? So that area is going to be, half of 25 is going to be 12.5. So I'll call that 12.5 meters. That's this rectangle here, plus I need the area of this triangle. Well, triangle is going to be 1/2, and the base of that triangle is 3.5 seconds, right? And then the height of that triangle is 25 meters per second. All right, so the seconds will cancel, and half of 25 is going to be 12.5 times 3.5. Gosh, I don't know what that's going to be. 12.5 times 3.5. All right, so this part here looks like it's about 40. That can't be right. Let me try that again. 3.5 times 0.5 times 25. 43. 43.75. Okay, so that's 43.75 meters, right? Okay. And then the other part is going to be 12.5. So 43.75 plus 12.5. And that gets me 56.25 meters. That's going to be my stopping distance. Okay? So the last question I want you to deal with is what happens if we double our speed in the beginning? Well, if we doubled our speed, then this area here is going to double, right? And then so that makes this area double. So that's going to be 25 meters if the speed doubles, plus and then that triangle how much is the area of the triangle going to go up by? Well, if you still stop in 3.5 seconds, but you're going, that actually wouldn't work because that question doesn't make sense. Because if you double your speed, you're going to be doubling the time it takes to stop. So you double your speed, you're going to double the time it takes to stop, and this area here is going to actually go up by 4. So that part doesn't make sense. I'm going to take that part out. So I know that it's going to take 56 meters to stop. And I know that if I went twice as fast, the time to stop would increase. So things would actually be a lot more complicated. It's not a simple answer. I'll show you more of that tomorrow in class. Anyway, I hope this helps. Again, don't worry about the part where if your speed doubles. We'll deal with that tomorrow. For now, try to understand what we did here and realize that the slope here tells us our acceleration. And that means that every second we slow down by about 7 meters per second. So that would be worth writing. Every second, car slows down by 7 meter per second. Now I'm just rounding that number. And know that the area of our acceleration graph tells us our change in velocity. Our change in velocity is a negative 25 meter per second. And the area of our velocity graph is going to tell us our change in position. So on this graph here, from beginning to end, we're looking at about 56.25 meters. So that's kind of interesting. Anyway, I hope that helps, and have a good day.